mathematical technique. This is a chemical equation given over here, a general form of equation. The rate of the reaction can be expressed either in terms of rate of disappearance of the reactant or rate of appearance of a product. The reactants are A and B, products are C and D. Here equation, recall the equation. The R stands for rate of the reaction. This symbol, differential expression, represents rate of disappearance of A. This one, rate of disappearance of B, rate of disappearance of C, rate of appearance of C, rate of appearance of D products. As you know, minus stands for reactants, minus for the reactant, plus for the products. Minus stands for decrease in concentration of the reactant with time. Plus stands for increase in concentration of product with time. And these coefficients will take the form like this. This 2 becomes 1 by 2, 3 becomes 1 by 3, 1 becomes 1 by 1, 4 becomes 1 by 4. So these equations are equal. This equals to this or equals this. All are equal to each other. The problem is set on this equation. Given the rate of disappearance of A, this value 2 into 10 to the power of minus 3 molar per second. Molar means concentration. Moles per dm cube are moles present in 1 liter. This value is given. This value is given. Calculate the rate of reaction. You can calculate the value of R. Use this equation and calculate. That is what you have done. R equals minus 1 by 2. This value is given. This you can simplify. Next is rate of disappearance of B. Use this R equals this one. Rate R equals minus 1 by 3, this one. The rate is known. R value is known, 10 to the power of minus 3. So equals minus 1 by 3 into dV by dt. What is minus dV by dt? Rate of disappearance of B. Cross multiply, you get this. This is the rate of disappearance of B. Next, rate of appearance of C. For the rate of appearance of C, use this equation R and this one. R equals dC by dt. So this is dC by dt as R. Both are same. Rate of reaction is same as rate of appearance of C. Therefore, this value rate of reaction is known. Is the one. That is the rate of appearance of C. Calculated. Next, for rate of appearance of D, use this equation and this equation. R equals plus 1 by 4 dB by dt. dt by dt. This R value is known equals, substitute this, calculate for this dP by dt. 4 into 10 to the power minus 3 molar per second. Rate of appearance of D. So this is how you can calculate. That is, for the given data, for all this, that is what is asked. So the problems like this also important from the point of examination. This is one set of problem. And one more problem we have. It is based on the half-life period, half-life change, time for half change. For that data, let us recall the mathematical expression for the half-life, the general form. Half-life of a reaction is directly proportional to A to the power of 1 minus n, where A stands for initial concentration of the reactant. Half-life. where n stands for the order of the reaction. So it says half-life of a reaction is a function of initial concentration, depends on initial concentration. Different initial concentration, different half-life periods. N stands for order of reaction. So let us write this for any two values. For any two initial concentration, when A equals A1, its half-life equals T1. When A equals A2, its half-life equals T2. Then takes the equation. This is the equation for this A1, T1, A2, T2. Divide this by this simultaneous equations. So left hand side by right hand side, you get this equation. This equation is same, but it is a function of only two values. It is a general function. So using this equation, we can, what is that, work out. That is, we can solve the problems, all these problems. These are the experimental data. Experimental data, you have to calculate the order of the reaction. For this data, 4 data are given. So using this equation, what is that? To feed the data into this equation and evaluate for n. Let us see that for the first one. So what is the first one is given? Half-life doubles when its initial concentration doubles. Let us write T1 equals T, A1 equals A, some value like this. Given the data, the half-life doubles. That is, T2 is a half-life. It doubles means 2 times this. When the initial concentration doubles, that is, A becomes 2A. Put this data into this equation. You have to feed this experimental data into this equation and go for evaluation of n. So that is what we have. When the initial when the initial concentration doubles, half-life doubles. Tt AA. Simplify and see that. Tt cancel, AA cancels. This gives 2 means 2 to the power of 1. 2 to the power of 1 minus n remains. The bases are same. Equate their exponents and calculate for n. N to this side, 1 to this side. N equals 0. This is 0 order reaction. So this data, for this data, the order of reaction is 0. Let us see for this data. Same way, let us in the same manner, let us solve the problem with this. Half-life remains same when its initial concentration doubles. Look at this. When the initial concentration doubles, half-life remains same, Tt only. A becomes 2A into this function and simplify. When you simplify, Tt gets cancels, that is 1 equals 2 to the power of 1 minus n. But 2 is there, can you express 2 as 2? That is 1 as 2, 2 to the power of 0. Because anything to the power of 0 is 1. So 2 bases are same, you can equate their exponents. 0 equals 1 minus n, n equals 1. First order reaction. Thus, for this experimental data, the order of reaction is 1. It is half-life period method. Let us see for this experimental data, what is the order of reaction. The same manner, let us do this. That is, read the problem. Half-life reduces to 1 by 4 when its initial concentration doubles. When the concentration doubles, half-life reduces to 1 by 4, T by 4. Its TA remains unresolved. When the initial concentration double, half-life reduces to 1 by 4, T by 4. This equation, the same power. Simplify. 1 by 4 equals this. Here 1 by 4 is there. We have to express 4 as 2 to the power of 2, denominator. If you take it to numerator, 2 to the power of minus 2. This is 2 to the power of minus 1 remain. Bases are same. Equate the exponents. Minus 2 is equal to this. and n equals 3, 1 plus 2. N this side, 2 this side, 3. The third order reaction. Let us see what is the order of the reaction when this is the experimental list data. Half-life reduces to 1 by 2 when its initial concentration increases 4-fold. Increase by 4-fold. The initial concentration is increased by 4-fold, 4A. Half-life reduces to 1 by 2, T by 2. The same expression. Look for N. It is 1 by T, 4 to the power of 1 minus N. Here 2 in the denominator, take it to numerator, 2 to the power of minus 1, and we have to express 4 as 2, 2 to the power of 2, 2 to the power of 2 into this. 2 bases are same. Equate the exponents. Minus 1 is equal to this one. Remove the bracket. 2 minus 2n. Minus 2n this side, minus 1 plus. So 2n equals 3, n equals 3 by 2. So it is 1.5, a fractional order. So this is the order for this experimental data. So this is how you can calculate the order of the reaction if you have the experimental data on the half-life period. The problems. Thank you.